hopefully you guys will see this as a nice talk for setting the stage. The original idea was to have it as a very in-depth, very long two-panel talk. I think that was very optimistic. So this will be hopefully a cool talk in kind of the history and the field of program analysis, how we got where we got and where we came from. Let's see, we're almost there. Is it 9?
Sure.
Can we have a countdown?
You can get started.
You start? All right.
The stage is yours.
The stage is mine. Psych, I'm not talking about program analysis. We're going to look at cats all day. But in all seriousness, when I saw that it was the 25th anniversary of DEF CON, I had this thought, because just the week before I read the CFP, I was reading some paper about program analysis that was published in the 90s, and I was thinking that, wow, these guys had like a lot of the same ideas that we're having now, and they were talking about this in the 90s. I wonder how much other such history has kind of fallen by the wayside. So I started looking a little bit, digging through it, and I wrote this proposal for the CFP to kind of go through the last 25 years of program analysis. And then when I was putting together the slides, I realized that program analysis goes way farther back. So where does, the 25 years number come from? And I thought about some more. I realized that 25 years is actually my involvement with program analysis. 25 years ago, my grandma gifted me a book called Professor Fortran's Encyclopedia, which had like a cat named X and a professor named Fortran and a caterpillar named Caterpillar. And it went through their adventures in computer land and taught kids all about computer. I was crazy about this book. I ditched classes in first grade to hide in the stairwell and reread this book over and over, and I learned BASIC from it, and then later on moved on to C and so forth, and I realized very early on that if I make a standard program that asks me for my name, and my name is too long, my last name, by the way, is Shoshitaishvili, so I actually triggered bugs with this last name, then the program would crash. So then, that turns out to be a buffer overflow and so forth. And then I started realizing that it's incredible to look at a computer program, try to understand how it really works. I mean, that's a whole different world in there, right? A world of ones and zeros and assembly instructions and logic gates. And somewhere along the line, it becomes alive and it becomes behaving and starts behaving in ways that you don't quite understand ahead of time. And that's manual program analysis, understanding how this works. But then you can take that and make it automated. You can create programs that can understand programs. And it's like a whole level of craziness. That's like creating some sort of intelligence almost. And that's what fascinates me about program analysis. That's what's kept me going down the path I've been going for the last 25 years. And so this talk is about, the history of program analysis, and it's about, why we want to do program analysis in terms of kind of the dry things, like we want to, hack programs, we want to make sure programs are safe, but try to approach this topic from the sort of kid's perspective of discovering a whole new world of how programs work and how programs might understand other programs. Program analysis is useful, but it's also kind of magical in a way. So with that said, let's move on to technical issues. Hold on. Boom. Success. Let's move on to program analysis. Program analysis is a field that has basically 3 parts to it, right? You want to analyze a program, but you always want to analyze a program to figure something out about it. So for example, you might want to make sure that a certain specification of the program holds. The program doesn't crash. The program doesn't allow random people to unlock your smart key for your house. The program doesn't allow, for your brakes to be remotely controlled and so on. And you have a goal that you want to achieve with that specification. So, for example, if your specification is, hey, I don't want this to crash, you could say, I want to make sure that specification holds always, or you want to say, you might want to say, I want to make sure that specification does not hold. I want to find the crash, right? So, kind of, are you looking for bugs? Are you trying to make sure things are safe? And then, of course, once you decide what you want to do, you need to decide how you want to do it. What is the technique that you're going to use to reason about a specification on your program? And with these three kind of categories in mind, I'm going to run you through the history of program analysis and where along the line we collected different items, kind of different instances of these three categories. And so we're going to commence on a brief history of computing starting in the 1830s with Charles Babbage. Charles Babbage created the analytical engine. It was a mechanical computer, super far ahead of its time, and he wrote a bunch of programs for it. By all accounts, these programs were actually really buggy, so that's really interesting. Some of the first computer programs written were already buggy. We didn't have that term yet. I'll talk about that later. And about a decade later, Ada Lovelace published a series of notes and more reasoning about this analytical engine, including the first program, the first complex program for one of these machines. So this is Ada Lovelace's description of the trace of the execution trace of this program. Right? And the program computed Bernoulli numbers. And so she goes through instruction by instruction and says how variables change and so forth. And this is in the 1840s, right? And so that's where things started. In 1947, about 105 years later, we got the term bug. Grace Hopper found people working with her found a actual moth inside a computer causing a computer error. So 100 years roughly after the first instance of kind of a computer in the semi-modern era, we have kind of this official term for the word bug. And this very quickly started getting people thinking about how do we kind of prevent actual software bugs. The moth, I guess, technically was kind of a wetware bug. But how do we prevent bugs in our software? And one of the kind of early visionaries here was Alan Turing, who's known for, of course, the Turing machine, but also cracking Enigma and onwards and onwards. But he also had the first paper that I could find that talked about, hey, maybe we should try to make sure that the program is correct, right? And he published this in 1949. So 2 years after the kind of invention of the term bug, people start thinking about how do we make sure that there are no bugs in a program. And this creates the field of program verification. So program verification says that, hey, given a program and its specification, we want to make sure that there are no bugs in this program, that this program carries out the computation it needs to carry out and so forth, and doesn't go astray. So as an example, here's a simple program that has a crash, but that crash is not reachable, right? So if you give this program somehow three numbers that add up where A plus B equals C, but then C minus B is not equal to A, it'll crash. And you want to see if this program is safe. You can run a program verification on it, which will identify, hopefully that this condition can never hold, and will produce a proof that tells you that the program is safe according to your specification. So that's great. And if everything worked like that in the real world, then we might not have bugs. And in certain cases, it does work like this in the real world. So there is formally verified hardware, according to a specific specification, of course. So things that the specification doesn't reason about, maybe still can go wrong with that hardware, but things that are covered by the specification don't. So there's, hardware that can provably not contain kind of timing side channel attacks, for example. And there's verified software. I heard recently that Google, for example, is switching over to a formally verified crypto system. And so the problems, of course, come when the software kind of gets bigger and complexity starts getting introduced, and verification stops being able to reason about things very effectively. So, for example, here we have a different type of program, right? And this program also doesn't crash. That A cubed plus B cubed equals C cubed, that's Fermat's last theorem, right? That is not solvable. There's no solution. But it took humans hundreds of years to figure this out, and the computer, verification tools, unless they're special coded for this, will also be unable to handle it. So it will kind of see this condition. It'll say, okay, well, if this condition is true, then the program will crash. Can I prove that the condition is always false? And if it can't prove that the condition is always false, it has no choice but to alert that the program cannot be verified. So what happens then, right? So then you have to go in and you have to start looking at the program manually and finding bugs. And if anyone's used kind of commercially available static analysis tools, you're very well familiar with the false positive problem, right? You open up a binary or a piece of software and the tool pops up alerts all over the place. And some of those are actual bugs, but you spend a lot of time chasing down the alerts. So when we looked at, software, open source software, for example, we often see, a security check done twice, the same check. If A is not null, if A is not null. Why is that check there twice? Because for whatever reason, a program verification tool alerted that there could be a bug there, and the programmer figured out some hack to make it shut up. So program verification, while it's a very useful field, like I said, there is verified software and hardware out there, it's not kind of the final answer on its own. So we also at some point need to have kind of the flip side. So program verification can say that is safe, but after that it says, okay, I can't really reason about it. So the flip side is you have a technique that says that is not safe. I can prove it, but I can't really prove, if it is safe, but if it is not safe, I'll give you a counterexample. And the way this works is by, finding counterexamples through whatever technique. So in this case, with a slightly different condition, that is A squared plus B squared equals C squared, a technique might find A, B, and C of 3, 4, and 5 as a counterexample that will reproduce a crash. And so this is, there are many techniques that we'll mention later that can be used to do program testing, but one of the very early ones, the first instance of program testing of this style that I found was in the 1950s, which is about 4 decades before I thought that this kind of idea was created. Programmers in the 1950s would program in punch cards, and to test their code, it was common practice to dig punch cards out of the trash and feed them as input to your program. This is unexpected input, just random stuff, and of course, if I had random stuff, your program shouldn't crash. So this is kind of an early example of this sort of kind of institutionalized testing that we're only seeing come back recently. And so there's early developments, verification, testing, the creation of those two ideas, and then the idea of what you might check for. So trash decks checked for crashes. Turing reasoned about ensuring logical properties. But this was all done manually. So this is kind of our first set of tools in our tool bag, and they're manual tools. We have to dig them out. Okay, let's get our trash cards. This one got eaten by something, and put in the ones that won't jam your machine and try them. But none of this was automated, and so as computers became more and more ubiquitous, the need for automation started showing itself. So again, we come on a mention of Grace Hopper here, because she not only found the first bug, but she also invented the compiler. So Grace Hopper in 1952 published a paper saying, hey, what if we wrote in kind of higher level languages and it got squished down to computer code? This took a little while to catch on, and the reason it took a while to catch on, one of the reasons, is that the code that was generated by this compiler was very slow. It couldn't be, optimized as well as handwritten assembly could at the time. And so this identified another need, another goal of program analysis, transformation of binaries into something different, something faster in this case. And in the modern era, you can transform binaries, for example, or transform programs to ensure that they're safe. You can transfer programs to meet any sort of specification and run on a different set of hardware. And so now we needed to optimize code because people write slow code when they're writing source for whatever reason. Another thing happened. People started realizing that we have all of these architectures with all of this data flowing around in them. And if you're not very, very, very careful, some data could be read from or written to a different location than intended, and the memory could be corrupted. So I just played 2 days of a CTF full of these errors, of course, memory corruption bugs. This was first described in 1968. In 1968, there was a paper saying, hey, we noticed that if the kernel, they called it a monitor at the time, blindly trusts everything that the user space sends it, bad things can start to happen. And so this paper introduced that concept. It's also the paper that, one of the early works in memory protection and virtual memory and so forth, which is pretty interesting that immediately they realized this was a problem. And a little while later, there was, Ken Thompson's Reflecting on Trusting Trust, where he reasoned that you could build in a backdoor into a compiler that could build in backdoors into sensitive code. And so suddenly we have 2 more things that we need to worry about in terms of specifications, or even more, but including memory safety, information disclosure, and authentication, right? So now you might want to verify that a program doesn't have a backdoor. Or you might verify that a program will not leak your sensitive private information. That one is very relevant today with all of our phones having all of our information and very little control over it. And so the need for automation was pretty well established by the kind of turn of the century for sure. But even before that, those papers was like in the 1960s or something, late 1960s, and very quickly, people started to meet this need. The research community started pumping out automated approaches, and so I'm going to introduce a couple of these automated approaches. Before I do so, I want to make you guys experts in program analysis so that we can reason about what's going on here. So we'll talk about a couple of prerequisites, right? So let's say you have a program. So on the top right, there's like a little Python program already That's already a vulnerable program, by the way. And so you have this program, and you want to analyze it. So you have to reason about a program in a slightly different way as a computer than as a human. So, for example, a program is viewed by a computer as a set of basic blocks. A basic block is a piece of code that is executed altogether before passing on control flow somewhere else. So in our case, we'll pretend that input is part of this basic block. So this x equals input is a single basic block, and then it might branch depending on the input, right? So if you put in 42, it'll do one thing. If you put in something else, it'll do another. And so this is the end of the basic block, and then the result of that if statement is two other basic blocks, the true case and the false case. And each of these has a constraint that has to be met, right? In order to go down one path, you have to put in 42. In order to go down another, you have to put in not 42. And so these are called constraints. If you then look at all of the basic blocks of a program, this is called the control flow graph, because that's, these are basic blocks and control flows between them. And if you look at a path down this graph, now in this case the graph is nice and simple, but in reality it could have loops. A path might hit the same node multiple times and so on. And then you look at the constraints all along this path. These are the path predicates that uniquely identified this path. So if you collect all of these constraints and you say that x is not 42, but x is 133.7, that input will, any input that matches those constraints will take the same path through the program. So these are kind of the prerequisites of our program analysis techniques. So now we'll go through three of them. Actually, for time reasons, we'll go through two of them and mention a third. But we'll start with symbolic execution. And symbolic execution got a lot of hype recently, especially with stuff like the Cyber Grand Challenge and so on, as a way for machines to reason about program code. And you think that this is something new, but it turns out that it's not. It's quite old, actually. So 40 years ago, a little bit more, the first symbolic execution paper that I could find was proposed. And there were several, actually, right in 1 year, basically. So this idea had some prerequisites that were met, and then it exploded. And so the symbolic execution engines were developed that could then symbolically execute Fortran code. Now we have symbolic execution engines that you can download off GitHub that can execute binaries, Java, Android, whatever you want. This is kind of a fairly powerful way of reasoning about programs. And let's run through an introduction of it with a slightly more complicated example than what we learned about program analysis with. Hold on. So here's a program that has several bugs, right? One is it definitely has one bug, and that is if you enter a username of service and a command code of 7, it'll crash, right? You can imagine that instead of this crash, it does some system relevant stuff, so it could be a backdoor instead of memory corruption, but basically we have a program with a bug and we would like to find this bug. So let's see how we might approach this problem with symbolic execution, right? So first let's look at the control flow graph of this program, starting from the beginning. And the control flow graph is made up of basic blocks and the control flow transitions between them. So we start at this input. If the input is service, it branches. If the username is service, it branches into one side of the equation of the program where it checks for the command code being 7. And if it is, it crashes. If not, it prints unknown command and then exits. On the other side of the branch, it asks for a passcode. If the passcode is invalid, it prints invalid passcode. Otherwise, it calls the authentication function. Then it prints exit and exit. So this is our control flow graph. And how would we use symbolic execution to try to find that crash, to try to find the ability to reach this crash. So we would start executing the program in an emulator. And in this emulator, instead of ones and zeros, we're working on X, Y, and other symbols, right? So, for example, username is a symbol in this emulator. So when we pull in an input, it'll produce an unconstrained variable called username. And we don't know what username is. Username can be anything because, that is how we implement our emulator. And as we check for values of username, we create what are called constraints, right? So these are the exact constraints of that the basic block checks when it pushes execution forward. And we collect two constraints in this case. On the one side, username equals service. On the other side, it does not equal service. These are constraints, and we continue executing both sides of this statement with symbolic execution. But then we hit something that is very bad for symbolic execution. We hit, for example, string processing functions. So a string processing function like A2I might check a given byte, see if it is a number. If it is a number, it'll do one thing. If it's not, it'll do another, right? Or if it's a certain number, it might do one. If it's not a certain number, it'll do another. So it'll keep branching the symbolic emulator at every, I'm sorry? Oh, awesome. It'll keep branching the symbolic emulator at every if statement, at every check on this number, until we get into a situation where there are just too many checks, right? So it'll try to check for a command code of, 10 bytes with arbitrary values, of 9 bytes, and so on. And there's an exponential path explosion here. And there are some approaches in the symbolic execution world to try to deal with this sort of path explosion. But in general, these approaches boil down to the requirement to remove paths, right, and lose this information. And so in the end, the symbolic execution engine might only find certain paths and not others and miss the bug because we had to simplify to keep things tractable. So that's symbolic execution. It might find the bug if you're lucky, right? But if you're not, and it has to simplify its state space essentially as it's executing, there are certain things that it might miss. Symbolic execution was proposed, as you saw, in 1975. But the interesting thing is that in Ada Lovelace's notes from 1942, we can see that she did a symbolic trace of the execution of her program. So where she has this sort of program execution log in her notes, she writes down the symbol, the equation for each variable as the program progresses. And this is the first symbolic trace of a program, done in 1842, before computers were invented. So that was a pretty interesting thing to find, and kind of a nice point of history that we can put as the start of program analysis in this sense. 1842, not 1975 or 1949 or any of those much later dates. And so symbolic execution is a kind of tool in our tool set that we can use to achieve either verification of a specification, the testing of a specification, or to support the transformation of code. Of course, how you verify a program, for example, using symbolic execution, is a pretty complex thing. With the symbolic execution style that I described, this for program testing, it generates inputs to find vulnerabilities, but it can't prove that there aren't any. But that's kind of we could go down that route for an entire semester course and not just a 45-minute introductory talk. So I'll leave that as future research for you guys. And we'll go on to static analysis, because static analysis can show that, for example, a program is immune to a certain class of vulnerabilities or properly implements a certain specification. Static analysis, or at least one of the very common ways to do static analysis, which is abstract interpretation, was proposed in 1977, shortly after symbolic execution. And abstract interpretation looks at the that should say abstract interpretation. Looks at the control flow graph, the program as a whole, essentially. It doesn't have to figure out how to reach a certain basic block to reason about properties of the program at that basic block, which is the problem that symbolic execution had, and the reason that symbolic execution could not find the bug in our example. And so static analysis with abstract interpretation might be able to find that bug, probably will be able to find that bug if it is a simple bug, for example, or actually I should say will be able to find that bug, because if it cannot prove that a piece of code is safe, it will raise an alert. The problem is that, as we talked about, there are false positives. So in our program, it might think that that function has a bug, even if it doesn't, alert on that, and eat up time for a human to go through and verify all of these results. And so through abstract interpretation, we got a way to perform verification of a specification on a program in 1977, 40 years ago. And then we moved on to fuzzing. And so fuzzing is kind of one of the biggest ways to find vulnerabilities in modern software, and it's actually surprisingly simple. Proposed in 1981 initially in its most basic form, which was, hey, let's throw random input at a program and see if it crashes. It's evolved quite a bit since then, and so the specific implementation of fuzzing that I'll describe here is implemented by American Fuzzy Lab. It's a fuzzer that mutates its inputs when it detects differences in program execution. And so let's see how it would run on our program here. We would start with some randomly generated test case or a human-seeded test case. So a human might input a username of ASDF and a password of 111. And that input will trigger certain basic blocks to be executed. Right, and so we executed the username input, of course. We executed the check for the kind of service username that could lead to the crash. We did not satisfy it, so we took the else branch, read in the passcode, and aired out on an invalid passcode, and exited. So we triggered those basic blocks. And so the fuzzer starts mutating this input, right? It might make a lowercase d a capital D or something, or it might mutate input in a way that passes another check. So it mutated the input in a way that passes that passcode check. It actually doesn't, because there's another bug in the program that I didn't notice before. But let's pretend that it creates a valid, size of a passcode, and triggers that authentication function, right? So that is a new basic block that it triggers. So now with fuzzing, we've triggered a block that symbolic execution before us wasn't able to trigger, just through randomly mutating inputs. But then we get stuck because through randomly mutating inputs, we are unable to satisfy complex checks, right? We need a username of service, and we have randomly mutated usernames. The chances are that we'll create the string service are very slim, and we'll keep guessing and guessing and guessing. Of course, in this specific case, you could seed the fuzzer with the string service, and you could scan the binary or the program for all of its strings, and automatically make the fuzzer pass this check. But string checks aren't the only complex checks in programs. There are hashes, There are complex input formats, dependencies between different input bytes. And so in the general case, we cannot guarantee, of course, with a fuzzer that we will find code that is protected by these complex checks. And so, fuzzing with this random data, of course, is a throwback to this trash stack concept. So, fuzzing was invented in 1950, not 1981, or at least manual fuzzing. So again, we find that program analysis techniques harken back to the middle of the century, and sometimes even farther to the 1800s. So now we have this kind of toolbox of a bunch of specifications that we can enforce, some goals that our analysis could try to achieve, and the technique through which we can achieve them. And next, we should evaluate them, understand how these different goals or how these different techniques help us achieve program analysis goals. And as a scientist, if you start thinking up an approach and you have a cool idea and you have a new program analysis technique, you want to evaluate it. So you want to take programs and specifications, feed them into your technique, and see how well it does. This is my clip art slide, by the way. So hopefully my clip art game is on point. So you run your analysis, you get your results, and you're happy, right? Well, there are a number of problems with this. One is that the analysis is more complex than you might think, because any program analysis has to deal with the environment of the program it's analyzing. And environments like Windows, Mac OS, Linux, mobile devices, cyber-physical devices, they have really complex environments. And having to model this environment even before analyzing, understanding how much better your program analysis technique is than previous techniques is quite a big investment that people often don't make or make in a kind of very fast manner. Another problem is finding a good data set to evaluate on, right? There's not really a good data set or there wasn't a great data set for vulnerability research. This problem is actually being worked on and new data sets are being created, as I'll talk about, but you need a good data set with ideally known vulnerabilities, so you can reason about how many of them your bug finds, and with variable vulnerabilities in different programs, so your technique isn't just specifically tailored for one style of vulnerability that you happen to detect, or one specific program that you happen to be very good at analyzing. Another problem is these specifications, right? Specifications in the real world are very complex, whereas specifications that you might want to use for your analysis tool initially in the early stages of development need to be fairly simple and ideally pre-provided. I mean, if you're looking at the analyzing something like Chrome and your specification is that Chrome should not leak user data to someone that should not get this user data, that's impossibly broad and impossible to enforce. Is your bank allowed to have your, various cookies or something along these lines? So you need a very good data set, standard data set with a very good standard implementation, standard set of specifications so that you can analyze how well your technique runs compared to different work, and compare those results to prior work, because that's a very important part of science and technical development, is understanding if you're making an improvement or not. And so we had problems as a analysis community in meeting all of these goals and having a good data set of applications with a good set of specifications on a good environment that wasn't too complex to implement, and that could produce results that we could reason about, that we could say, okay, we have ground truth data for the vulnerabilities that are actually in this data set, and we detect X of them, or we manage to rule out vulnerabilities in code that has no vulnerabilities, and so our program verification is correct. And so there, like I mentioned, there have been several projects to solve this problem, to create these data sets, and one of these projects essentially was the Cyber Grant Challenge. If you guys were here last year, you probably saw all of the Cyber Grant Challenge, hoopla, where for the first time in history, 7 fully automated program analysis machines fought each other in a game of capture the flag. So the same game that I spent the entire weekend playing and only got 4 hours of sleep is the game that machines who didn't need to sleep played last year rather. And these machines, of course, suffered from all of the problems that I just talked about, the environment problem, the specification problem. And so the Cyber Grant Challenge created a custom operating system with very specific vulnerability specifications to evaluate these systems. Now, for the actual competition, of course, the source code wasn't available. Since then, they released the source code, so you can really look at the source code, understand the vulnerability, and then reason about how well your tool finds certain vulnerabilities across 249 binaries. So it's a 249 programs. So it's a data set that has a lot of variance. There are a lot of different types and different difficulties of vulnerabilities. And all of this is freely available for people to analyze their tool and understand how well it does. That's my other piece of clip art. So the Cyber Grant Challenge and the programs that were written for this, these 249 programs making up the Cyber Grant Challenge data set, allowed us to do what I call, to perform what I call the program analysis nursery experiments. So I see the Cyber Grant Challenge data set as the nursery of program analysis, where you can reason about different improvements for different techniques. So for example, symbolic execution on the entire data set finds 9 vulnerabilities. This symbolic execution as implemented in Anger, which I'll talk about in a sec, which is an open source binary analysis program available on GitHub. But symbolic execution on this entire data set finds 9 vulnerabilities. That's not a lot, right? There are vulnerabilities in every program of these 249 programs. It only finds vulnerabilities in 9 of them. Of course, we can optimize symbolic execution using various tricks. So Anger supports, for example, concrete execution when there is no uncertainty in the state, when all the data is known, or when there are constraints on all the data. And so by utilizing all of these optimizations, we can get 26 crashes in 26 binaries. Utilizing static analysis, so combining symbolic execution with variant testing, which is a technique created by Carnegie Mellon University that utilizes parts of abstract interpretation to help with symbolic execution, we can push that up to 31. So I should say here that this is our implementation of variant testing, and it might be suboptimal. So their variant testing might be considerably better. But that all pales in comparison with fuzzing, this seemingly simple technique of throwing random data and seeing what happens, finds 106 crashing binaries in the data set. So this gives us an idea of where program analysis is, and this is a good showcase for the simplicity of evaluating all of these different analyses on this data set and reasoning about the results, because now we can look at them in terms of summation numbers, but there's also some subtleties there. They find bugs different types of bugs in different binaries. So we can look into that and make inferences and try to create new approaches. So for example, we looked at the difference in the types of bugs that symbolic execution found and that fuzzing found. And we realized that they have very different coverage. So the types of the basic blocks that fuzzing can trigger are very different from the basic blocks that symbolic execution can trigger. And sometimes one finds a crash, sometimes another finds a crash, sometimes neither of them find a crash, in fact, very frequently. And so we decided to combine them in a very straightforward but careful way. And the idea is as follows. We begin by fuzzing the binary. This is nice and fast and achieves decent code coverage, but as we discussed, eventually gets stuck on complex checks. And then we use symbolic execution to find the constraint that can get through that check, but possibly suffer from other limitations of symbolic execution and not find the actual bug. And then we synchronize that back into the fuzzer. We synchronize the knowledge of how to bypass the complex check back into the fuzzer, and it continues to mutate that input until it finds the bug. And we do this iteratively, back and forth between the fuzzer and symbolic execution. So by implementing symbolic assistance for the fuzzer in this way, we achieve on this entire data set 118 crashes. And an interesting thing is here is that we have this 118 crashes in the data set, but if you take the union of all of the different techniques, all the different techniques have crashed something like this from memory, 150 to 160 binaries. So there's a lot of uniqueness between the different techniques used here. Driller, the applicability of it varies by program, whether or not there are complex checks. We can run through a quick run here. So this is a control flow graph of an example program, and Driller starts in the top left corner there. And it first starts by fuzzing a portion of the program before it gets stuck in a complex check. And this is the basic block coverage on the right in this graph here. You can see it just kind of flat lines, right? So then if we run the symbolic execution engine to help the fuzzer reach extra code paths, it allows us to find just a little tiny bit more basic blocks in the execute some more basic blocks in that control flow graph of the program. And if we keep invoking the symbolic execution engine to help the fuzzer get unstuck every time that the coverage flatlines like that, we eventually drill into the program deep enough to find the bug. And so that's how Driller works. There's still a lot to do. So there's this whole red area that however many programs, about 100 programs that we have never exploited before, that we've never crashed before using any automated techniques, which represent missing tools, basically, that humanity has yet to develop, or at least we have yet to develop. And so if this all sounds interesting to you, I encourage you to join in. There are several ways that you can participate in program analysis research. One is you can contribute to open source frameworks. So we run one of these frameworks in our research lab. It's called Anger. Go to anger.io. There's a lot that we could use help with: documentation, environment support, better techniques, and so on. And the other is that I'm always looking for students. I'm starting as a professor at Arizona State University. I just finished a PhD at UC Santa Barbara, and both of those places are incredible places to go to if you want to do research in program analysis or in general security. So if you're thinking about graduate school, or you are curious and want to do an internship, reach out to me. I'll put you in touch with the right people, and you could explore that. The presentation is available online. All my contact info is right here, and I guess we'll do questions in the hall. Awesome. Thank you, guys.